In this lesson, we're going to learn about arithmetic sequences. Now, this is just a specific type of sequence, and a sequence is a pattern of numbers or a collection of an ordered set of numbers where each of those numbers is referred to as an element. Now, each element that's in this sequence is given a subscript based on its location in that sequence. So let's say we'd look at the pattern of all even numbers. Well, notice 2, 4, 6, 8, 10, they all follow this pattern. And eventually, at some point, we know that we're going to get to 80, and we also know that this continues on forever. So each number or each element in this sequence is referred to by a sub 1, a sub 2, a sub 3, meaning that this is the third term of the sequence, and so on. Sometimes we just refer to it as A4, A5, A6. So a few different types of sequences are as follows. When a sequence has an infinite number of terms, it's obviously referred to as an infinite sequence, and that's denoted by these three dots referred to as ellipses. And so this does follow some pattern. It looks like if I start at 11 to 15 to 19 to 23 and so on, it looks like I'm adding 4 each time. And by putting these dots at the end, it's showing that this sequence goes on forever. As opposed to this sequence right here, where we list all of the elements inside of these braces, and there's a stopping point here. It doesn't go on forever. So this follows the pattern from -9 to 9 by going in multiples of 3, and therefore this is a finite sequence. If we take a look at this one, 0, 1, 0, 1, 0, 1, it just keeps bouncing back and forth between one value and another. This is referred to as an alternating sequence. But notice that all of these original sequences, the first two anyway, seem to be increasing. We saw the even numbers seem to be increasing, but it's possible for sequences to also decrease to where it looks like we have to subtract 5 to get to each of these terms. And so we're going to take a look at a particular type of sequence referred to as an arithmetic sequence. So sequences can be defined by a rule that basically is similar to a function in a way, to where with functions, f of x equals 3x minus 2, I would be able to replace the x's with any value that I chose in order to get the output. So plug in any input and you get the corresponding output. With sequences, on the other hand, notice that they have a different notation. They're referred to as a sub n. And now we are only allowed to plug in positive integer values. And that integer that we plug in is describing the location in that sequence. So let's say we wanted to find the first term of the sequence, or in other words, a1. Well, that just means replace the n value with 1, and we find out that a1 equals 1. The subscript of 1 just tells me the location in that sequence, so if I take a look at a2, that's going to give me a value of 4. A3, by plugging in 3, gives me a value of 7. So the third term in the sequence is 7. The fourth term in the sequence is 10. And so this pattern would continue infinitely, and therefore I could find the 100th term in the sequence if I chose to, by simply plugging in 100 to n. Now, one pattern that we should notice here is that after you plugged in each of these numbers, this is our sequence rule, it looks like by plugging in the values of 1, 2, 3, and 4, we got the first 4 terms of the sequence. And it appears that all of these are off by 3. That if I just continue to add 3 to get from one term to the next, then I should be able to get the next term by just adding 3 again. So if I look at the function rule, or the sequence rule rather, I see that the coefficient of n seems to be that common difference between the terms. 4 minus 1 gives me 3. But so does 7 minus 4, and so does 10 minus 7. Now I'd also like to take a look at what would happen if we were to plug in 0. This would be the term before the first term. In other words, sometimes we refer to it as the 0 term or the 0th term. And if we plug in 0, notice that it's going to cancel out that first term and give us -2. Well, you should notice as well that that -2 is actually referring to the A0 value. So in our arithmetic sequence rule, it appears that the n is going to be multiplied by the common difference, and the number added or subtracted from the end is our 0 term. Now notice that we're only able to plug in integer values, so it doesn't make any sense for us to say a sub 2/3 or a sub 3.4. We can only plug in integer values because the value is telling us the location in the sequence. So any sequence whose consecutive terms have a common difference, like this particular sequence here, is referred to as an arithmetic sequence, and that common difference is called D. So in this case, D is 3, but to find that, we would simply subtract any two subsequent terms. So A2 minus A1 would be 3, but so would A3 minus A2, that should also be D. A4 minus A3 should also be D. So in general, we should realize that for an arithmetic sequence, any term in the sequence minus the term that comes right before it, a sub n minus 1, will always be the same common difference of D. Well, now we have a sequence and we'd like to come up with the sequence rule. So the first thing to recognize is that each of these numbers is off by 4. If I add 4 to 6, I get 10. Add 4 to get 14. Add 4 to get 18. So the common difference is 4. And we refer to that as D. So remember that the common difference was the coefficient of n. So why don't we make a guess that a sub n is equal to 4n? And let's just test it, see if that actually works. That would mean that if I plug in 1, I get 4. If I plug in 2, 4 times 2 is 8. If I plug in 3, 4 times 3 is 12. If I plug in 4, 4 times 4 is 16. And so sure enough, this common difference is 4, but we've got a slight problem because I was supposed to get 6 as my first term, but I got 4. I was supposed to get 10 as my second term, but I got 8. I was supposed to get 14 as my third term, but I got 12. So it appears that even though this is relatively close, it looks like each of my values in my sequence are 2 higher than these numbers. So I should simply add 2 to each term by saying 4n plus 2, and therefore that would be my sequence rule. So let's take a look at what A0 would be then. If I were to plug in A0, notice A0 would be 4 times 0 plus 2, which is 2. Well, that makes sense because notice that in this case, it's not coincidental that the constant rule would work because the 4 is the common difference and the 2 is what A0 would be. And we could see that from here. If I were to take 4 away from 6 to get the term before the first term, that would give me a value of 2. So with this function rule, or this sequence rule rather, we can calculate the 100th term. Without having to find the first 99 terms, we can simply plug in 100 to n, and we get an answer of 402. So for an arithmetic sequence, we now have a general formula for how to create an arithmetic sequence. We take the common difference times n, and we add c. But wait, d is the common difference, while c turns out to be A0. And we could find A0 if we have the sequence by just taking the common difference of 4 away from 6. Now, an interesting kind of property of sequences or arithmetic sequences is that if we know the common difference and we know one of the terms, we should be able to find any other term that we want. And the reason for that is that we're simply adding a certain number of d's to get to a particular term. So if I want to find A2, then I just simply have to start with A1 and add the common difference one time. But notice, what if I wanted A3? Well, I would still start with A1, and now I would have to add D 2 times in order to get to the third term. But what if I wanted A4? Well, I would start with A1, and I would add the common difference once to get to A2, twice to get to A3, and 3 times to get to A4. But this also works with any terms that you're given. Let's say that I'm given A6 and I'd like to find A10. Well, notice that 10 is 4 terms away from the 6th term, so I would need to add D 4 times. Let's say we have the 12th term and we'd like to find the 28th term. Well, now we just simply have to add 16 D's because there are 16 terms between the 12th term and the 28th term. If we have the 40th term and we want the 75th term, we simply add 35 D's. So this type of property is what's going to allow us to have any terms within a sequence and find the remaining terms. So let's say that we have the 4th term, which is 16, and the 10th term is 46. That means that A4 is equal to 16, and A10 is equal to 46. Now we don't directly know what the common difference is, but we can use a little reasoning here to recognize that A10 can be found by starting at the 4th term, which we're given, and add D 6 times. Well, we have A10 as 46, and we have that A4 is 16. So now the only unknown is D, which means if we subtract 16 to get 30 and divide by 6, we get that the common difference is 5. Which means that if I start with A4, I could find A5 by just adding 5 to it, and then continue to find more terms by adding 5 over and over. But we'd like to find the 70th term, and the only way we could really do that is if we come up with a sequence rule for A sub n. So we know that A sub n should be 5 times n plus some quantity. And so what we could do at this point is take any of the values that we know. For instance, we already know that the 4th term is 16, and therefore we could plug in 4 for n. So we get A sub 4 is equal to 5 times 4 plus c. But A4 is equal to 16, so why don't we replace that with 16 equals 20 plus c, and therefore the missing constant is negative 4. Now remember that negative 4 also represents what the 0 term is of this sequence. But once we have these two values, we should know that the sequence has a rule of 5n minus 4. Now we could find any term in the sequence that we want. We want the 70th term in this case. So we simply plug 70 in for n. 350 minus 4 is 346. So now let's take a look at a series. Now a series is simply a sum of the terms in a sequence. So if I were to have a sequence, let's say the sequence of even numbers, then the series would be 2 plus 4 plus 6 plus 8 and so on. Now the story goes that there was a prolific German mathematician named Gauss, Johann Gauss, who was asked by his teacher in elementary school to add all of the numbers from 1 to 100. Now I like to think that the teacher was probably just giving the class some busy work while the teacher maybe graded. And within a couple of minutes, Gauss came up with the answer of 5050, which was correct. Now it wasn't that he could add numbers really quickly. It was that he came up with a pattern for adding all of the numbers from 1 through 100. Now he could have started by saying 1 plus 2 is 3, and then 3 plus 3 is 6, and then 6 plus 4 is 10, and so on. But instead, he decided, why don't I reverse the numbers underneath this original sequence? And the beauty of this is, if you now add each of these values straight down, 1 plus 100 is 101. 2 plus 99 is also 101. 3 plus 98 is also 101. So he noticed that if he added that first and last number, that he ended up getting the same value of 101 100 different times. 100 times because there were originally 100 numbers. Well, notice that if I wanted to find the sum of the first 100 terms, we refer to it first of all as S100 or S sub 100. And what we should realize is that it's really just 100 101s. So we can multiply 101 100 times. However, that's not quite my answer. Because notice, if you take a look at the list of the green numbers and the orange numbers, we added those values twice. We just wanted to find what the sum of the top row was. But in order to find this, Gauss ended up reversing the numbers underneath. And so since we're adding these values twice, we have to divide the final result by 2. And what we've done is created a formula for being able to do this. So 10,100 divided by 2 is in fact 5,050, and he was correct. And from that point on, Gauss was able to now come up with this formula for doing this for any arithmetic sequence. He first of all started by taking the number of total terms, which in this case was 100 terms. He then added the first term and the last term, A1 and AN. A sub n is whatever term you're on, or whatever the last term is. And now we simply divide by 2 in order to get the final result, because we added the list twice. And therefore, in general, what we've done is we took the number of terms, then we multiplied that by the sum of the first and last terms. 1 plus 100 is 101. Once we have that, we divide by 2. So let's do an example then of finding the sum of the first 30 terms of the sequence that happens to have this rule. Well, taking a look at our formula, we obviously know that we're going to need the number of terms. So n would obviously be 30. But we're also going to need the first term and the last term. In other words, we're going to need to plug in 1 to that rule, which gives me negative 3 plus 4, or 1. And then we plug in 30 to that rule, which is negative 90 plus 4, or negative 86. We can now say that the sum of the first 30 terms is the number of terms, which is 30, times the first term plus the last term, which is 1 minus 86, and divide that whole quantity by 2. Now notice that 2 goes into 30 15 times, and 1 minus 86 is negative 85. So all we have to do is multiply in order to find that the sum of the first 30 terms is negative 1,275. We didn't need to know all of the terms in the sequence and add them up one at a time, because this process or this formula that Gauss came up with will get us there in a much faster way. So just remember that this sequence, or this formula, only works for arithmetic sequences, and arithmetic sequences are very particular types of sequences where each term is off by a common difference.